Good day, students. This time around, we are going to be talking about the addition rule of probability and the multiplication rule of probability. And so, two things, and we'll work on some problems as well. So, let's get started. So, the first thing we want to talk about is a definition. What's a compound event? A compound event is where two or more simple events are combined. Okay, that's it. That's a compound event. Nothing major, just something you want to be aware of. So let's look at the addition rule now. The addition rule is when written this way formally. It's the probability of A or B, two events, A or event B, and it's equal to the probability of A plus the probability of B minus the probability of A and B. All right. And so we're going to do some problems and talk about all of these at once and give you some idea of how to do them. But this is the formal addition rule. Or we should talk about the meaning of the word or. It's really a set theory word. And if you've done any computer programming or anything, it's an inclusive or. Inclusive, which means that if I say let's say Zach or Angie went to the store, okay? Then there are really three meanings to that. The first meaning is Zach went to the store by himself. The second meaning is Angie went to the store by herself. And the third meaning is Zach and Angie went together. And so that's what we mean by an inclusive or. It includes the case where they both go together. All right? So Zach individually, Andy individually, Zach or Angie, and then Zach or Angie could mean that both. So it basically means either or both. Okay? And that's the meaning in this particular statement. Now, this is the thing I'm probably going to have in my notes. It's a formula I need to be able to use and recognize on tests. All right, so let's do a practice problem. Okay, this here is for problems 9 through 20 in the homework, and you're being assigned some of those. I may actually end up doing the same one, but in general, this is to get some practice. You should, of course, always look over all the problems just in case you see one you've never done before, so you know how to do it. Okay, so let's have an example of an OR problem here. Okay, here we go. Okay, so I'm going to look at problem 12. And problem 12 says, if one of the high school drivers is randomly selected, find the probability of getting one who did not text, or they drove when drinking. Okay? So that's the problem. They did not text while they drive, or they drove when they were drinking. Okay? So this is an or probability, and so the key is that it's an or. So this is really the probability of no text and driving, or drive and drink. Okay? So it's an or probability. And so our answer is going to be the probability of no texting, okay, plus the probability of driving and drinking. Notice instead of using A and B, I like to actually kind of describe it a little more. That helps me to do it. And then minus the probability of no texting and driving and drinking. Okay? So, how do we do that problem with this table of values here? So, what we notice is that we have some pretty high numbers. We have 731, 156, 3054, and 4564, all and they're all separate categories. So to get a probability, we need to get a relative frequency. And so to do that, one of the things we need to do is we need to add these up to get the total number of people who were in this survey. So this will give us the total, right? And if you remember, or if you wish, the number in the sample space, how many are in the sample space? Well, it'll be the sum of all this. So this will be 15, carrier 1, that'll be 20, carrier 2, that'll be 15, carrier 1, that'll be 8. So there were 8,505 total people in the survey. And so I need to find the probability of somebody who did not text. And to find that probability of not texting, okay, what I see is the no texting people are these people right here, okay? It's that group of people. So I need 156 plus 4564, which is 10, 12, 7, 4. I have 4,720 people who were not texting. So 4,720. And the probability would be over the total number in this particular survey. So there's my probability for not texting. Okay, so now we move to the next one. And the next one is we want the probability of those who drive and drive while drinking alcohol. And so that would be the yes group here. So that would be this group of people who actually drove while drinking. So 731 plus 156 is 788. That means there were 887 of them divided by the total 8,505. And so now we have the probability of that group. And so finally, we need to subtract the number who are not texters and do drive while drinking. And so that is just this group. You'll notice how it's the overlap between the other two. But then that probability we subtract is 156 over 8,505. And so if I add these numbers together, and I'll let you do that on your own, but I take 4720 plus 887 minus 156 over 8505, I'll get a number, and then I can convert that to a decimal, and I now have my probability. And so that's how you tend to do these problems. Now, one way you can make it easier is if you're doing or and problems, is you could make totals in your table. And so, like this. And so this would be the total of the first row right here, and then the second row. And you'll note, and then this is the first column and the second column. And then this would be the total of everything. All right. And now notice the total of everything, this would be 8,505. And we use the second row for the first probability, no texting. And we use the first column where you actually drink and drive. And so that would be one way to do this problem is you just get the row and column totals ahead of time, or you can do them separately like I did here. And so there should be no problem adding this to get the probability answer, but that's how you do an OR probability. Now, there are other ways where it might show up where you get where they might have a tree diagram or some other issues like that. And so just moving the problem here, you'll remember in class we pulled socks out of the drawer, right? We had a drawer, we had a sock drawer, clean sock drawer, and we had 20 pairs of socks. We had 10 blue, I believe it was 8 red, and 6 green. And so we can make a tree diagram of this experiment. So on the first sock that we take out, it's blue, red, or green. And then on the next sock we take out, it always depends on what happened on the first sock. But in any case, no matter what happened the first time, we're going to still pull out a blue, red, or a green. All right. Now, because we're wearing our socks, this is going to be a without replacement problem. In other words, we're going to keep the sock out and put it on our feet, which means that the probabilities will change. But in any case, you can do an OR problem here. What's the probability that I would get a blue probability of a blue or a red sock, okay, on say for second sock, okay? So in other words, on our second draw, what's the probability of getting a blue or a red? So we'll talk about how to label these tree diagrams in a moment. Well, I might do it now. But to get a blue or a red for the second sock, well, I could get a blue or a red here, could get a blue or a red here, and I could get a blue or a red here. So it's this one, or it's this one, or it's this situation. And of course, that depends on what you got for the first situation, okay? But we're just asking, what if you got a blue or a red on the second sock? And so you would look for the situation where you get a blue or a red, and then your branch would be labeled with the probability, and then you could use those probabilities. Okay. And so we will talk about how to label tree diagrams. We'll get a little better problem later. I just kind of made this up on the spur of the moment. But you can talk about OR probabilities using a table like we did here, but you can also use a tree diagram. And there are some specific situations. You could have said, what's the probability that I get a matching pair of blue socks or a matching pair of red socks? Okay. Say it's 4th of July and I want patriotic colors. Okay. And so if that's the case, then a pair of blue socks, that probability is going to be that branch, blue, blue, and a pair of red socks is going to be this branch, red, red. And so you would then follow the OR probability problem and then write out the probabilities based on that, based on your tree diagram. Okay. And there's a lot more to this, and we'll get to that as we move along. So anyway, there's your first example. So what we want to do now is we want to give another definition, and that is of the term disjoint events. So what that means is that the events cannot occur at the same time. So if we get back to the sock example, for instance, in that case, when you draw out a sock, you get either a blue sock or a red sock or a green sock. And you don't get a blue-green or a blue-red sock. You don't get both at the same time. So those events cannot occur at the same time. Another term for this is the term mutually exclusive. So if you hear me use it, I mean disjoint. Okay? So these events have nothing in common. All right? They can't occur at the same time. They're disjoint. All right? If you think about the other problem we did, nothing there is actually disjoint, because you could be somebody who texts and drives and drink and drives, or you text and drive but you don't drink and drive, etc. So those events could all actually occur at the same time. All right? And so you have to think about problems and pay attention to that. All right? If something is disjoint, then the probability of A and B is equal to 0. Okay? Because it can't occur at the same time, and we're going to talk about this, but the word and means at the same time. And so if that's the case, these events cannot occur at the same time. Therefore, the probability of them occurring at the same time is 0. Okay? Now, if you have complementary events, if you remember, the complement of an event is everything not in the event. Okay? So if you have complementary events, A and A bar, all right, and they are disjoint. Complementary events are always disjoint, mutually exclusive. Why? Because they don't have anything in common. They have all the stuff that the other one doesn't have. Okay? And so none of it matches up. So they're disjoint. So you could say the probability of A and its complement is always equal to 0. Okay? But you could also say a couple other things which are good probability statements to remember. You can say that the probability of an event plus the probability of the complement is always equal. That's 100% or 1. Okay? And once you can say this, then you can say the probability of A equals 1 minus the probability of the complement. Or if you wish, the probability of the complement is equal to 1 minus the probability of the event. And that just comes from this natural statement. Okay? Now, there's quite a bit theoretically there. And so what we want to do at this point is look at a quick problem. Your text gives a great example of this. If 90% of households have a cell phone, and then that's that's event A, then what's the probability that you'll grow up in a house without a cell phone? Okay. So that's the probability of the complement. Well, that's equal to 1 minus the probability of A. So I always write the formula when it happens, and then I fill it in. Well, the probability of having a cell phone is 90%, so you'd have 1 minus 0.9, or 0.1, which is equal to 10% of the households will not have a cell phone. Okay? And so this would be the probabilities at that point. Okay? Let's go to the multiplication rule. Okay. So here's the formal formula for the multiplication rule. It's the probability of A and B equals the probability of A times the probability of B given that A occurred. All right? This here is called a conditional probability, and we'll come back and talk more about conditional probabilities in subsequent lessons. All right? So this is a formal rule, and we'll kind of go with ad hoc definitions at this point. So a couple of things. A and B actually has two meanings. Okay? One of the meanings is if I said Adam and Ryan went to the store. Okay? Adam and Ryan went to the store. Then that meaning, I understand that if I was watching this event occur, I would be seeing both Adam and Ryan going to the store at the same time. Okay? Whereas with the or situation, I have three circumstances. With this one, I have the understanding that both are going at the same time. Okay? So the Adam and Ryan event occurs at the same time, and so they both end up going to the store. All right? So that's one meaning. And then the second meaning is that I could have thought about Adam and Ryan going to the store, but I could say, oh yeah, and I'm answering your question. Did any students go to the store in the past week? And then I would say, oh yeah, Adam and Ryan went to the store. And so what it means in that context is that maybe on Monday, Adam went, all right, and then on Wednesday, Ryan went. And so you can still say Adam and Ryan went to the store, but you have this sort of sequencing that one of the things occurs and then the next thing occurs. All right? So both at the same time, or one occurring and then the next one occurring. So that's the meanings of A and B. All right? So let's look at a tree diagram because I think that's the best way to understand B given A. So let's look at that real quick. So back to the sock drawer. Whoops, draw that drawer again. Sock drawer. There we go. Green sock this time. But in the sock drawer, we had blue, red, and green socks that we drew out on the first draw. And then on the next draw, we are going to end up drawing out blue, red, and green socks as well. Okay. And so what would be the probability of getting a blue sock given that you got a green sock on the first draw? So what branch would I pay attention to? So this refers to the second draw based on what happens in the first draw. So it's second draw versus what happened in the first draw of the socks from the drawer. So in other words, my first draw has to be a green sock. And then I want to find the probability of the blue one given that I took a green one first. Okay? So this means we're going to have to start labeling those probabilities pretty quick, because if we start seeing these conditional probabilities, we need to know how to find them. Okay? So before we go on, there is a small idea we need to talk about, and that is the idea of independent or dependent. All right? And so, two events are independent Yeah, I'm sorry. Okay, I'm sorry. I got clicked off there. Hit something with my thumb. Fat hand. So, independent again. What's independent event? An independent event is when you have two events and they are independent if the probability of one does not affect the probability of the other. Okay? So, probability does not affect probability. All right? Dependent is essentially if they're not independent, it just means not independent. Okay? So, what would be independent or dependent? Now, just so you know, if I'm going to wear these socks, when I pull a sock out of the drawer and put it on my foot, the probabilities are going to change. So if I had 6 green socks at the beginning, 6 green socks, and I had a total of 20 socks, okay? So 6 out of 20, that would be the probability of drawing a green. And therefore, 8 out of 20 for the red and 10 out of 20 for the blue. But if I put that sock on my foot, then I'm pulling socks out of the drawer without replacing them. And so what happens? The if I drew a green on the first one, I had 6 out of 20. But on this draw after I drew a green, I now only have 5 greens left, and I only have 19 total socks. So the probability of this second green one is going to be 5 out of 19. So this event occurring changes the probability the next time around. And if that happens, then we are not independent. If the probability does not affect, then you're independent. Okay? And so that's kind of the key idea. All right? And so with socks, you're always keeping a sock and then trying to get the next sock. All right? And this probability, this 6/20ths, will change the probabilities of the red and blues as well. Because even though I didn't draw a red and I still have 8 reds, the denominator changes from 20 to 19. I now have a slightly better chance of getting a red, and the same for the blue. And so being able to label these tree diagrams, understanding with or without replacements, really helpful, and that can help you get a multiplication rule. And so let's do a problem now. So when I look at this problem, I'm drawing the socks out. Here's my diagram. I now know the whole sample space, and that's why I drew the tree diagram. But now what I want to do is I want to label the probabilities. So I knew that there were 10 blue socks to start. There were 8 red, and there were 6 green. Now, we've already done this one here. The green is 6/20ths there, and then if I get a green the next time, that'll only be 5/19ths. And then the red will be 8/19ths, because I'll still have 8 red socks, and the blue would be 10/19ths, because I'll still have 10 blue socks. Okay? So now we can go and we can fill out the next branch. Let's do the red branch. And so 8 of these are in the drawer, and so I have an 8/20. Okay, so I made a mistake before. If I have 10, 8, and 6, I actually have 24 socks, not 20. So the first thing I need to do is I need to go and change my denominators. And I'll fix that right now. And I apologize for that. Who knows why I said 20? It's just one of those days. Anyway, so I would have a 6/24 chance of getting a green. So what I wrote the previous page with 6/20 was incorrect. It should be 24. Always make sure you get the total. Don't just assume what it is. And then I would have 5 green socks left over, but only 23 socks to draw from. So the probability changes. Still not independent. And then in the same way, I would still have 8 reds out of 23 socks and 10 blues out of 23 socks. Okay? And you'll notice 10, 8, and 5 add to 23. That's why the denominator is now 23. And so if we move on, and we do the red socks, we have 8 out of 24 are red, and then we only have 7 red left and 23 socks left at that point. So 7 23rds. We still have 6 greens, so 6 23rds, and we still have 10 blues, so 10 23rds. And then we do the blue column, and that will be 10 24ths to draw blue the first time. The number of blues changed to 9. The number of total socks changes to 23. And then reds, it will then be 8 out of 23, still have a total of 8, and the greens will be 6 out of 23 because I actually drew a blue sock. And now this is a fully labeled tree diagram. And so if I want to know the probability of getting, say, a red sock and then a blue sock like this, a probability of red-blue is really the probability of a red and then a blue. So a red on the first draw and a blue on the second draw. So see, notice how it's sequential. I need the first one to happen and then the second one also is happening. All right, so this is one of the meanings of probability, okay, for this situation. And so since it's an and probability, the formula is then going to be the probability of a red times the probability of a blue, given that the red has already occurred. Okay? And so what are those going to be in terms of my problem? So the probability of a red essentially is the probability of a red on the first draw. And so that's going to be 8 24ths. And then I'm going to multiply that times the probability of a blue given that the red happened on the first one. So that means we go down this branch to this probability, the blue, given that the red already occurred. And so that becomes 10 23rds. And so therefore the whole probability is, and I'm going to cancel my fractions here a little bit. This is 1/3. And so that makes it a little easier. So I get 10 69ths, and then I can write that as a decimal using a calculator. And so that is now the probability of getting a red and a blue. All right. These events are the first draw and the second draw are not independent. Okay. Because the first draw changes the probabilities on the second draw. Notice the denominators change and some of the numerators change. And because they change, that means the one thing occurring affects the next thing. All right? And so, therefore, they're dependent rather than independent. Okay? So you have to kind of keep that straight. All right? Now, that's a good example of that problem. And this is the multiplication rule in action. Now, I want to go back and I want to mention, we had the problem, where we had yes for drunk drivers and we had no for drunk driving. And then we had text drivers and no text drivers, right? And so when you have a table like this, if they ask you the question, what's the probability that you are a text driver and you have no drinking and driving? Well, in that case, just like we did on the earlier problem, you kind of go, oh, text drivers are this, no drinking and driving are this, and where those overlap, where they cross, is going to be, in this case, the number of people who text and don't drink and drive, okay? And then you can put that over the total. So we would just pull that number. And this is where both of them are happening at the same time versus one happening after the other occurs. So these are the two ideas of and probability. Okay? One more thing. Last thing, another way to say things are independent is if the probability of A and B is equal to the probability of A times the probability of B. Okay? Now, and so this is just a check. If this is not the formula for and, it's just saying that the probability of B given that A occurred is actually equal to the probability of B in this case. And so if this thing happens to be true, our formula for the multiplication rule changes to this. And if this is true, that means the two events A and B are independent. All right? And so that's something that you want to keep in mind. So usually if we do with replacement, those kinds of problems will be independent. Okay? And let me see if there are some other problems here. They do have a few other examples. I encourage you to look at the birthday example, and we'll probably do a problem with that. They do some significance, and they talk about the rationale for the multiplication rule. But I think this video is getting long. I think we've got through kind of the main ideas. And then let's talk about questions. So work on these problems before class on Wednesday, and we'll go from there. All righty, talk to you later.